And for our final video for section 4.1, we are going to be talking about two of my favorite topics, two of my favorite types of numbers, prime and composite numbers. Another just great tool for developing number sense, getting a good sense of prime numbers and composite numbers. So one way to classify whole numbers is to examine their factors, and again, building these rectangular arrays. So what I'm going to do is show you a picture of a couple different numbers and all the different ways that we could use their rectangular arrays to sort of look at these numbers. So I'm just going to paste up this picture. Two different numbers, 16 on the left and 30 on the right. So here we have 16 and here we have 30. And what I want you to do, this is going to take you a few minutes. Pause, and I just want you to stare at these pictures, and I want you to notice things, observe things, and I ask you the question, what observations can be made and what conjectures could be made from these rectangles? Remember, conjecture, an unproven theory or idea, right? So just notice things. Go ahead and pause and take note. So here's an example of something that you could have observed. For the number 16, based on these diagrams, the arrays, we can state that the numbers 1, 2, 4, 8, and 16 are all factors of 16. Because you can make an array with those numbers on the sides of the rectangle, right? So 1, 2, 4, 8, and 16 are factors of 16. And similarly, 1, 2, 3, 5, 6, 10, 15, and 30 are factors of 30. That's one thing you could notice, one observation you could make. Another thing you might have noticed is that the factors of the numbers kind of occur in pairs, right? And so what do I mean by that? You've got 1 and 30 here, and then 1 and 30 here, right? Two different ways to show the rectangle, right? Or the factors, 1 and 30, two different rectangles. Same thing, 2 and 15, 2 and 15. So there's a pair, right? So you got these two that are the same, these two that are the same. 3 and 10, 3 and 10. So these two, and then you have 6 and 5, and 5 and 6, and these two, right? Is that true for 16? Kind of. 1 and 16, 1 and 16, so those match up. 2 and 8, 2 and 8, so those match up. But what happened here? Oh, so 16, what's special about the number 16? 16 is a perfect square. It can be written as 4 squared. And so if a number is a perfect square, it doesn't have a pair, right? A pair of factors, right? There's only one version of it. So this one had 5 drawings, and this one had, what, 8 drawings, okay? So maybe that's something that holds true for perfect square numbers. Maybe they would have an odd number of arrays, right? Another really important one is this. It's almost as if we are duplicating the factors. If we're just trying to determine what are all the factors of 30, right? What are all the factors of 30? And we start drawing these pictures. I'm going to erase some of these lines I drew. If your question is, what are all the factors of 30? And you draw this picture, and then this one, 3, 4. So you draw them in this order, 5, 6, 7, and then 8. If you draw those, And your goal was just to find the factors. My question is, did you have to draw all of those pictures? And if not, when could you stop? Well, we only had to do these first four. After we got to 5, we started to duplicate factors. We found that this was, right, 5 times 6, but 6 times 5 is really the same thing. It gives us the same factors. And so once we get here, then we start to just repeat, right? Things we already knew. And the same thing occurs with the number 16. Once we got to what? 4 times 4? Once we got to here, then we started to duplicate factors. And so once we get to the squarest version, this or this, the squarest version of our array, then everything else beyond that is a duplicate factor. Why are we talking about this? Well, because it's going to come in handy later, okay? Once we start to get to some of our prime number tests, that factor we just talked about, that's going to come in handy. All right, so let's talk about the number 94. Let's talk about the number 94. And what I want to do is notice some things about it. Okay. First question is it a perfect square? Messy handwriting. It's 94 a perfect square? Maybe you know that, maybe you don't. And so we can kind of prove it. Well, we can say we know 9 times 9 is equal to 81. And we know the next possible combination is 10 times 10, which is 100. And 94 is between those two numbers. So no, 94 cannot be a perfect square. Okay. So what I want to consider then is what do we know about the dimensions of rectangles that would have an area of 94? Or if we were making an array and we wanted 94 pieces in it, what do we know about the rectangles? Is there some conclusion that you could draw based on some of this information over here? Well, 94 is less than 100. Agreed? Which means all of our sides here have to be less than 10. Why is that? It's because of what we talked about up here, right? Once we get to the squarest version of our number, right? The squarest version of our array, then they just start going down again, right? The factors start going down. And yeah, and that's exactly what I wanted to say. And what I was really asking about was the squarest versions of these, right? Well, obviously, if we were making an array, we could make one that was 1 by 94. So we could certainly have one side that's longer than 10. But the other side is going to get maxed out. Once we get to that squarest array, they're going to start decreasing again, right? All rectangles for 94 will have at least one dimension less than 94, right? So one side will always be less than 10, okay? Now, if we started to check those, right? If you started to draw out all your arrays for 94, what you would end up with is actually only 2 options. The one that I showed here, 1 by 94, and the other one would be 2 by 47, would also make 94. So what does that tell you? The factors of 94, are the numbers that we were able to draw. 1, 2, 47, and 94. 1 here, 2 here, 47 here, and 94. What are those lengths and widths of your arrays, right? So that's this idea of how do we find the factors of a number using the arrays, and also like how can we draw some conclusions about the side lengths, right? And so the point is, if you go back to, and I apologize, I just described it poorly there for a minute. If we're looking at the squarest version, what would be the dimensions of that? Here, obviously 30 is not a perfect square, but 6 times 5, right, is really close to 6 times 6, right, which would be greater than that. So you're never going to have a side length, or one of your side lengths is always going to be less than 6. That's kind of the key idea there. Okay. And again, we're going to come back to that in some later discussions in this video. So now let's start talking about the difference between prime and what we call composite. This picture kind of sums it up well. So if we look at the number 11, and I say, make an array for the number 11, how many options do you have? How many ways can you do it? That's really the only one, right? And this is something that a young learner can comprehend. The only way to multiply to be 11 is 1 times 11. Well, if we say the number 10, and I say make arrays for that, you got 2 options, that one or that one. 1 times 10 is equal to 10, but so is 2 times 5. And so this is how we can sort of easily explain the concept through visuals and manipulatives of what we call a prime number, or what we call a composite number. Prime numbers have exactly 2 factors. Okay, so prime have exactly 2 factors. Okay, 1 and itself. Composite numbers, they're composed or made up of additional numbers. So these have more than 2 factors. So that's what we mean when we talk about prime numbers and composite numbers, and it's illustrated very clearly here in this sort of diagram. So here's a list of numbers up through 12. And you can see by making a little list like this, and young students could do this considering these arrays. You start with your number, and then you start to list all the factors, right? So you might make arrays for all these different numbers, and you would come up with the fact that, say, 10 has factors of 1, 2, 5, and 10. 8 has factors of 1, 2, 4, and 8. 12 has factors of 1, 2, 3, 4, 6, and 12. And then you count the number of factors they have. And what you'll notice is some of them only have 2 factors. Those numbers, 2, 3, 5, 7, and 11, those are our prime numbers, right? Those ones that have only 2 distinct factors are our prime numbers, 2, 3, 5, 7, and 11. So here's a definition. Prime and composite numbers. Any non-zero whole number with exactly 2 factors is called a prime. Non-zero whole numbers with more than 2 factors are called composite. Now, you might have been wondering this question already. What about the number 1? 1 is neither. 1 is neither prime nor composite. How many factors does the number 1 have? Only 1. It doesn't fit into either of the definitions. So 1 is neither prime nor composite. So just take a moment then and continue that table from 13 to 20. List the numbers 13 to 20 and determine whether they are prime or composite. So as you can see here, I sketched them out. I just wrote the numbers. And then if I could come up with some other multiplication problem that equaled the number, that's going to tell me if it's composite, right? 14 is equal to 2 times 7, so that's composite. 15 is equal to 3 times 5, so that's composite. 16 is 2 times 8, or even 4 times 4, so that's composite. 18, 2 times 9, or 3 times 6, so that's composite. And then 20, 4 times 5, or 2 times 10, so that's composite. So that leaves the other numbers. What are our prime numbers? 13, prime. 17, prime. 19, prime. They had no other factors. Now, you might even be wondering questions because mathematicians have wondered about primes and studied them and investigated them for hundreds of years. One of their questions was, is there a largest prime number? And there was actually about a 70, 80-year period from the 1800s to the mid-1950s where the largest known prime had 39 digits in it. It was this number right here. So this number was, again, the largest known prime number for about 80 years. Since then, computers obviously make it much more feasible to determine whether numbers are prime, because there's a lot of mathematical calculations that go into it. But now the largest prime numbers, the number of digits, the largest ones that are known, number into the tens of millions, right? Tens of millions digits long. And so there are really big numbers that are prime. So what I'm going to have you do is play with some numbers. And my question to you is it prime? Everybody's favorite game show, is it prime? Take a moment, pause, see if you can determine if those numbers are prime or not. So you might have been wondering, how do I do that? How do I determine if a number is prime or not? It really comes down to divisibility. Can a number divide into those numbers? And didn't we just talk about in the previous video divisibility rules? Yeah. If that's now jogging your memory, maybe you pause and try these again. Number one, 43,101. Maybe you try some of those divisibility rules. Remember the divisibility rule for 3? Let's add the digits. 7, 8, 9. If you add those numbers, you get 9. 3 is divisible by 9. So that means 3 is divisible by that whole thing. So 43,101 is a composite number. That's a composite number. Is it prime? No, not prime. As long as you can find one number that it's divisible by, not prime. How about number 2? This should have jumped right out at you, I hope. It's an even number. If it's even, 2 divides it, not prime. What about 53? Is 53 prime? Maybe this one you were not so sure about. And so we have to talk about ways we can check to see if a number is prime or not, if none of our divisibility tests work, right? And it really comes down to those same sorts of rectangles that we drew earlier. Remember these, fellas? Remember these, right? And remember how we talked about once we got to a certain point, we started to duplicate factors. Once we got to here, we had already found all the factors, so we didn't need to go any further. And so there is a way we can do this. So I'm going to show you kind of my approach, and then I'll give you kind of a formal divisibility test rule. So if we take the number 53, and here's where you use your calculator, right? You're going to use your calculator, and what you're going to do is you're going to start dividing it by prime numbers, right? So you're going to divide by prime numbers. Divide by primes to check. So we're going to divide 53. And we're going to start with the smallest prime number, which is 2. Now we know it immediately that that doesn't work because it's an odd number, but I'm still going to do it. I'm going to pull up my calculator so we can see this. Let's pull this over to the side. And so if we do 53 divided by 2, we get a decimal, 26.5. So that basically means that it's not divisible by 2. So we haven't proved anything yet. We just know that it's not divisible by 2. Well, then we're going to divide it by 3. 53 divided by 3 is 17.6 repeating. 17.6 repeating. Okay. Next prime number is 5. 53 divided by 5 is 10.6. Notice how we keep getting decimals. Now we'll divide by 7. 53 divided by 7. 7.57 something. 7.57 something. So now I'm going to ask you a question. How far do we have to go? How far do we have to go? What we've noticed here, what I want you to notice is look at the numbers we're dividing by and look at the answers that we're getting. We're starting off small and these are big. But as we go down this list, these numbers start getting closer and closer together, right? They start making things that are a little bit squarer. Agreed? If we go one more here, the next prime number would be 11. What you're going to notice, 53 divided by 11 is 4.81. And notice how the number we divided by is now bigger than the number we got as an answer. This is the point where we can kind of stop, because as these numbers continue to get bigger, these numbers are going to continue to get smaller. And we have actually already checked every number less than 4.81 that could possibly work, right? And so actually we could have even stopped a moment before that, okay? We could have stopped a moment before that. And the reason why is this idea of square. If you think about the number 53, and what is the next biggest square number beyond 53? Well, 7 times 7 is 49, and 8 times 8 is 64. So 64 is the next biggest perfect square beyond 53, which means the thing I described poorly earlier is that at least one of the sides of this rectangle, if there were one for the number 53, one of the sides would always have to be less than 8, right? It would always have to be less than 8. And we saw that happen right here, right? Once we got to this point, 7 times 7.57, it didn't work. And so once we get to that point where, we've already checked all the possible numbers less than 8, we can stop. We can stop and we say, we know that 53 must be a prime number, right? Because it's not divisible by anything. We check 2, we check 3, we check 5, and we check 7, and we didn't need to check anything bigger than 7, because anything bigger than 7, right, we already determined wouldn't work, right? And so if we start to try to put that into a formal definition, it kind of looks like this. This is what we call the prime number test. So it says, suppose n is a whole number and k is the smallest whole number such that k times k is greater than n. If there's no prime number less than k that is a factor of n, then n is a prime number. I know that sometimes we have to pause and reread these several times. I'm going to try to make it a little bit easier for you. Let's say n is equal to 13. We're going to use a smaller number to work with. N is a whole number, 13. K is the smallest whole number such that k times k is greater than n. So here's what I was doing earlier up there. So what's the smallest perfect square that's greater than n? Wouldn't it be 16? 4 times 4 is equal to 16, which means in this case, k is equal to 4. It couldn't be 3. 3 times 3 is 9, and that's less than 13. And this says it has to be greater than 13. Okay? So again, the number that we're analyzing is 13. K is this number 4 that exists. And if there's no prime number less than k, that's a factor of n, then n is a prime number. So this is the maximum, right? That's sort of the maximum number that you have to test to when you're checking to see if 13 is prime. So you would try 13 divided by, well, what are all the prime numbers less than 4? 2 and 3. That's it. So as long as 13 is not divisible by either of those, this is going to be like 4.3 repeating. It's not, then 13 must be prime. So that's our test. Let me summarize that. If you're trying to test to see if a number's prime, you're going to divide it by prime numbers. You just have to know when to stop. That's the key. And this is the rule that tells you when to stop. You find whatever the next perfect square would be beyond the number that you're testing. And whatever the square root of that number is, k, in this case 4, you don't have to go any bigger than that when you're testing your prime numbers. Okay? So let's have you try it. Two questions. Is 421 prime or composite? And is 667 prime or composite? Pause and try those. All right, let's try 421. Let's take a look at 421. What did you come up with? So again, we're going to take the number 421 and we're going to just divide it by a bunch of prime numbers. We're going to divide it by 2, and then we're going to divide it by 3, and then we're going to divide it by 7. We're just going to keep going. The question is, how far do we need to go? How many numbers do we need to test? Well, the biggest number that we have to test is what? Did you figure that out? The biggest number you have to test is 19. Why? Because 21 times 21 is equal to 441. 441 is larger than 421. So 21 is the maximum, right? Once you get to 21, you stop. And the last previous prime number before 21 is 19. So if you check 2, 3, 7, 11, 13, 17, 19, and none of them work, which they don't, then 241 is prime. All right. So all this rule, this prime number test, it's all about finding what that highest prime number is, or that last one that you need to check. What about 667? Okay, 667. Well, same thing. 667 divided by 2, divided by 3, divided by 7. Keep going. When do we need to stop? Well, what did you come up with? What was that next highest perfect square beyond 667? 26 times 26 is equal to 676. So your max is 26. So what's the last prime number before 26? 23. And if you divide 666 by 23, you get 29. 23 and 29 are factors of 667. which means 667 is composite. Is it a prime number? No. So again, the prime number test is all about dividing by prime numbers. All right. So the last thing is just a little bit of a history lesson. And it's another way to sort of check to see if a number's prime or not. So the Greek mathematician Eratosthenes created this method of determining prime numbers. And his method is called the sieve of Eratosthenes. And so essentially, we're just going to be crossing them off. So if you want to play along, you can do so too. So the way we do this is we start off by just crossing off the number 1 because as we've already determined, that's not a prime number. So then we go and we say, okay, well, what's the first prime number that we know? 2. So we're going to circle our 2. I'll highlight our 2. So there's our very first prime number. Well, then you go through the entire table and you just start counting or crossing off every multiple of 2, because every multiple of 2 is composite by definition. So I'm going to go ahead. I'm just going to cross off every multiple of 2 in this table. So that was fun, but it's done. As you can see, it essentially just eliminated half the numbers from our table. So then what you do is you say, okay, well, the next number that's open on the chart must be a prime number. And then you go through and you start eliminating, crossing off every number that is a multiple of 3 that you haven't already crossed off. So 3, and then 6, and then 9, and then 15, and then 21, right? And so now that they're spaced out a little bit, and again, you're counting by 3s, and it's sort of like every other one is going to get crossed off. So I'll go ahead and complete that on my own. All right, so the 3s are done. And next we'll go on to notice that 5 is our next open number. And so then what do? We go ahead and we cross off all of our numbers that are multiples of 5. So what do we have? Well, everything in the 5s column that's not already crossed off will get crossed off now. All of these. And anything in the 10s column is already crossed off. So then we go to 7. And now we have to go through and say, okay, do we have any multiples of 7 that haven't been crossed off yet? Well, count by 7. 7, 14, 21, 28, 35, 42. There's one, 49. Cross off 49, 56, 63, 70, 77. There's one. 84. There's one. 91, 98, 105, 112, and looks like 119. I think I got the rest of them. Okay. So my question to you now is, before I go any further, is how far do we need to go in crossing these numbers off as far as like checking? We know 11 is going to be our next prime number, but for the size of the table that we have here of 120, how far do we have to go as far as counting? Consider the previous scenarios that we were analyzing. What I'm going to do is I'm going to continue this while you think about that. So the number 11, if we think about multiples of 11, that would be on this diagonal: 11, 22, 33, 44, 55, 66, 77, 88, 99, 110. And that's actually it, right? We didn't have any to cross off. Can we stop already? Well, consider the largest number in this table is 120. What's the next perfect square beyond 120? Do you know? 11 times 11 is 121, which means that every other number on this chart, every other number on here is going to be a prime number, right? Every other number on here is going to be a prime number because we've already crossed them all out. We've already crossed off all of the numbers that are, again, less than those, right? If I asked you, is 89 a prime number? Well, you would divide it by prime numbers up to the point of the next biggest perfect square and whatever that root is, which would be 100. The root is 10. We've already done all those. 121 is 121 or 120 a perfect square. We would only consider numbers less than 11. We've already done them all. So what does that mean? It means that every other number on here is a prime number. So isn't that interesting? We actually only had to check multiples of the first 11 numbers to identify every perfect square that up to 120. All right. So you won't necessarily have to have all of these prime numbers memorized, but what you should be able to do is be able to check pretty quickly whether or not a number is prime through just some division with your calculator, but then also knowing when you have to stop.